Hello and welcome to Network Theory. Today we are going to speak on source transformations. References Ravi Singh, William Haidt. Now, coming to our topic, which is on source transformation. What is source transformation? When you have a circuit with multiple sources, that means you can have voltage, combinations of voltages and current source in the circuit. It would be helpful if you make it into all voltage sources or all current sources and then solve the circuit. So hence we would require some kinds of transformations. So when we speak about source transformation, current sources in parallel can be added to get a resultant current source. So when we are having something like this, for example, a circuit where you have got some resistances and two current sources. So you have a 5 ampere current source, you have a 2 ohm here, 2 ohm here, and this is a 1 ampere current source. So the direction of the arrows are in the same direction as so these current sources are in parallel and they are in the same direction, so they can be added. The resultant will be 6 ampere parallel to 2 and 2 are in parallel, so effective circuit can be reduced to a 1 ohm and 5 plus 1 6 ampere. So this would be a resultant circuit. Similarly, this is the case of current sources. Now if these directions are opposite, so if the 1 ampere current had been flowing down, then you would end up with a 4 ampere. So in that case, so effective or the algebraic sum you would take for the for finding the resultant current source. Similarly, when we have voltage sources in series can be added to get the equivalent voltage source. So here voltage sources, obviously we know when we are using, suppose we are using batteries. So in that case, what happens is that batteries which are in additive polarity gets added together, whereas when we have in a subtractive polarity, which means that suppose you have some two voltage sources like this connected like this they are connected in series and they can be added together. They have, this is negative and this is positive, so additive polarity. So if this is V1 and this is V2, you can get a V1 plus V2. Or if both are this these are in I mean the same signs are coming together, then you would have a additive, or you would have a V1 minus V2 or V2 minus V1, whatever. So effectively, voltage is the point being that current sources in parallel, you can add them up, and voltage sources in series, you can add to get a equivalent voltage source. Now, when we are converting from a voltage source to a current source or a current source to a voltage source. So now here we are speaking about current source to voltage source conversion. A current source is normally represented with a resistance in parallel to it. So this is your current source. Now, these are the terminals, suppose. This is can be, so you can see that the current can flow through the resistance providing a voltage drop which will be equal to I into R. So when you're converting this into an equivalent voltage source, this becomes equal to V and resistance R in series with it. Now what is the value of this V? V can be found out as I into R. So a current source in parallel to a resistance will be equal to a voltage source which has the value of I into R, but the resistance is going to be in series because obviously a voltage source has a series resistance with it. So the condition is that the current source has to be in parallel to the resistance, otherwise you cannot convert it. In similar way, a voltage source can be converted to a current source. So the voltage source, if you are seeing, the voltage source is like this in series and it is represented with in series with a resistance. So this can be converted to an equivalent current source which will be equal to, the current source will have the same resistance in parallel to it. Now what is the value of this current source? This I will be equal to V divided by R. So a voltage source in series with a resistance will be converted to a current source which is equal to V by R in parallel to the resistance. Again, the condition is that the voltage source must be in series with the resistance. Then only you can convert it to a current source. Now, basically, when we are summarizing source conversions and rules, the first goal is that we end up with, in a circuit which has got multiple sources, we end up with all as current sources, or all can be voltage sources. Now, for the current source, the head of the arrow corresponds to the positive terminal of the voltage source. So, when you're converting a current source to a voltage source equivalent, so the current source, the arrow is corresponding to the positive terminal of the battery. Or in other words, you can say the current is flowing upwards, and if the positive polarity, the current always flows out from the positive polarity like this. So, effective current direction is going to be the same for the voltage source. So, the head of the arrow is basically corresponding to the positive terminal of the voltage source. Now, current sources in parallel can be added, voltage sources in series can be added, like we said. Now, so this we have already seen that when we have current sources in parallel, which you can convert them to an equivalent current source with parallel to a resistance. Similarly, the voltage sources in series can be added. Now, if the voltage or current associated with a particular resistor, this is a very important point which is used when we have a dependent source. So now when we have a dependent source, we had spoken about dependent sources. Dependent sources depend upon some other voltage or current in the circuit. So if the voltage or current associated with a particular resistor is used as a controlling variable, then it cannot be included in a source transformation. For example, if I just consider something like this, or suppose if I have a 10-volt source in series with a resistance of 2 ohm, and then I have a current source which is equal to 2I. There is something again a resistance parallel to it of 2 ohm or so. Now, the point to be noted is that if the current I, now 2I is a it is a current dependent voltage source. It's a current, it's a current source which depends upon a current. So it's a current dependent current source. Now this current is flowing through the 2 ohm resistor. Now, if you have to solve the circuit, we can use different techniques. One is source transformation. Now, the source transformation will convert this voltage source, which is in series with this 2 ohm, to a current source. Now, the problem is that the current I is what is controlling this current source. So, the element which is through which the current flows, which is the 2 ohm resistance, cannot be involved in a source transformation, which means that you cannot do a source transformation on the 10 volt plus 2 ohm, not possible. That means I cannot convert it to a current source using the 10 volt and the 2 ohm. Why? Because this current is what is controlling this. So if you are using source conversion, then the circuit changes. So that is not possible. So you have to retain this element as such. You can maybe do a source transformation here. Source transformation can also be done on dependent sources. This is to be noted. So you can do source transformation on dependent sources, right? But source transformation on those elements which are controlling the dependent source is not possible. This is one point we need to know. So this is all about source transformation. So now let's see. Okay. So this problem is on current sources which are connected in parallel. Now you can see that there is a 3 ampere source and a 5 ampere source which are in the same direction, and at the same time there is a 1 ampere source in the opposite direction, but all are connected in parallel. So as we have seen, if they are connected in parallel, they can be added together, added or subtracted depending upon the direction. So you can add the 3 and 5 amperes together, which gives you an 8 ampere, 1 ampere is in the downward direction. So the effective current would be 7 ampere in the upward direction. So 3 plus 5 minus 1 would be your equivalent current in the upward direction. So 7 ampere. At the same time, you've got 2 ohm and 2 ohm in connected in parallel, which gives you a 1 ohm. So effectively, the circuit reduces to this 7 ampere with 1 ohm in parallel. So the 2 ohm and the 2 ohm, these two ohms which are in parallel are going to be having an equivalent resistance of 1 ohm. This can also be converted to a voltage source. So I'm going to be converting this to a voltage source. Now, the voltage source would be 7 ampere and 1 ohm in parallel will give you a voltage value of 7 into 1, 7 volt. The 1 ohm resistance is going to be in series. So this is how it is going to be. So here, the value of the resistance is 1 ohm and the value of the voltage source is 7 volt. So this is how you convert it into a voltage source if it required. So depending upon what is the requirement of the circuit, you can make the circuit into a current source, equivalent current source, or a equivalent voltage source. Okay. So here the next example is with dependent sources. Now what we can see is that in here an independent source of 20 volt is there and a dependent source of value 3i. Now 3i means it is a current dependent current source. So the arrow shows that this is a current source which also depends upon a current I. The I current flows through the resistance 2 ohm which is connected as shown. So as we discussed earlier, if any element, if the current through any element is controlling a dependent source, then this element cannot be used in a source transformation, which means that I cannot convert this 20 volt which is in series with 2 ohm. So maybe we could have converted it into a current source, but this is not done here. Why? Because the current through the 2 ohm is what is controlling the dependent source. So if you do a source transformation over here, it would change the circuit as such. So normally what is done is we retain this element as such till the end. That is what is normally done. So now how do you solve this? Different methods are there. One method using source transformation, if you are solving it, then you can go for converting this current source. So the 3i current source is in parallel to the 2 ohm resistance. So these two can be converted to a voltage source. So current source in parallel. So dependent sources also can be converted to can also be converted using source transformation. So this is what we are going to be doing here, converting the 3i and 2 ohm. So this effective volt, if I convert it to a voltage source, then this becomes 3i into 2, which is a 6i voltage source and with a 2 ohm in series. So let's redraw the circuit now, doing this changes. So I'll keep the 20 volt and the 2 ohm as such. Now the 3i, the current source and the resistance, these two are going to be converted to a voltage source. So the voltage source is going to be, now see the arrow of the current source, it is pointing upward. The arrow corresponds to the positive polarity. So I'll show this with the positive polarity up on the top and negative polarity downwards. So here 2 ohm and the value of this is 3i into 2 is 6i, right? And this is the value of, and this is the current which is flowing through the 2 ohm. I'm retaining it as such. So basically what has been done is here the 3i into 2 has been converted into this voltage source with the 2 ohm in series. Now this has become a simple series loop over which KVL can be applied. So I'm going to be applying KVL here and I'm ending up with 20 minus 2i minus again 2i minus 6i is equal to 0, which means I get 20 minus 10i is equal to 0, or effectively current I is equal to 1 ampere. 20 minus, 1 minute, 2 plus 2, 4, 4 plus 6, 10. 20 minus 10I, or I is equal to 2 ampere. Yes. This is how we calculate this, right? So by doing a source transformation, it has been seen that, so here the source transformation was done over here. So understand that you can do source transformation on dependent sources also, but source transformation cannot be done in this case with this source and the resistance of 2 ohm. Why? Because the current through that element 2 ohm is what had been controlling the dependent source. So current source transformation is not possible here, but you could do it here, right? So this is one example where we have solved it using source transformation. Okay. So this example is again uses source transformation, and the question is to find Vx. Now, what is Vx here? Vx is the voltage across the 4 ohm resistance, right? And through which a current I is flowing. So this Vx is what is controlling this current source. Now, here we have a current source which depends upon a voltage. So it is a voltage controlled current source. So which means that since Vx is controlling this, you are not supposed to change this element. So this element is to be retained as such, right? So which means what? You can do source transformation, etc. on the other elements, but not at this particular element. So now let's try to solve this. So here we can also see, that there is a 2 ampere in parallel to a 2 ohm, which can be converted using source transformation. Again, 8 ohm parallel to 1 ampere. This also can be converted to a voltage source. We have another current source, which is a dependent current source parallel to 1 ohm. So we saw already that dependent sources also can be converted using source transformation. So I'll be converting this also to a voltage source, which means we'll finally end up with a all voltage source combination network, right? So now let us try to redraw the network. 2 ampere and 2 ohm. This I'm converting it into a 4 volt with a resistance 2 ohm in series. The 4 ohm is also, this 2 ohm has come in series here after conversion, after making it into a voltage source. Now there is a 4 ohm resistance already over here. So that is also going to be, so that is your 4 ohm resistance. Then I'm redrawing the circuit as such, 6 ohm. Now comes this part where you have the current source in parallel to the resistance. So this 2 Vx and 1 ohm is going to be again converted to a voltage source. What would be the value? It would be equal to resistance into current. So 2 Vx into 1, which is a 2 Vx voltage source with a 1 ohm in series. Now the direction of the voltage source, the polarity direction, arrow corresponds to the positive. So likewise, let us again redraw the network with the resistance 1 ohm, or maybe show the polarity first. Let us show the voltage source first. Doesn't make any difference, but let us draw this way. So this is 2 Vx into 1, which is 2 Vx with the 1 ohm in series. Then there is a 4 ohm here. This is the 4 ohm across which the voltage is Vx, right? And now we are coming to the this part where you have 8 ohm and 1 ampere in parallel. So this is again going to be converted to a voltage source, which makes it equal to 8 volt and 8 ohm, 8 volt. Fine. So now we are ending up. So there is now here a 6 ohm, and there is 6 ohm is in parallel, sorry, in series with a 4 volt. So that can be again converted back to, so 4 volt in series with a 6 ohm resistance can be again converted to a current source. So that makes it 4 divided by 6, which is 2 by 3 ampere, 4 by 6, and the resistance obviously comes in parallel. So the resistance is 2 plus 4. Remember that this is 6 ohm. 6 ohm is in parallel to this 6. So that makes it 3 ohm. So now pre-drawing the remaining part as such, minus 2 plus and 2 Vx, that is this 5 ohm, 5 plus 8, 13 ohm, 1 ohm. Let me just show it like that only so that there's no confusion. Plus minus 8 volt. Now this 4 by 6 is in parallel to this 3 ohm, which can be again converted back into a voltage source. So 4 by 6 into 3 gives you 12 by 6, which is 2 volt, 2 volt voltage source in series with a 3 ohm. So which means, so here you can see this is a voltage source, this is a voltage source. If I convert this also to a voltage source, we have an all voltage loop network. Simple KVL will, a simple series loop will come through which a current of 1 of I ampere is flowing. So it was already shown that the current through the 4 ohm is I, and the voltage across this is your Vx, which we are supposed to find out, right? So the next step would be to apply the source transformation over here and make this into one loop. So redrawing it, I'm showing a 2 volt source in series. So this is a voltage source. So the resistance has to be now in series. So that was 3 ohm, and we have the remaining part which is equal to, so we have a minus and plus 2 Vx in series with, and 1 ohm, a 4 ohm, this 8 ohm, and the 8 volt source. So now we have a simple loop, right? And the current flowing through the 4 ohm was I, and the voltage across it is Vx. So basically when we solve this, I've got 2 minus 3I minus 2 plus is a plus 2 Vx minus 1 plus 4, that is 5I minus 8I minus, this is 8 volt, minus 8 is equal to 0. So this gives me 2 minus 3I minus 5I minus 8I. This makes it minus 16I, then minus 8 plus 2 into Vx. Now what is Vx? Vx is equal to, this is your Vx, which is equal to nothing but 4 into I, right? So substituting that, 2 into 4I is equal to 0. Or I get it as 2 minus 16ai minus 8 plus 8I is equal to 0. Or this is minus 6, and minus 16 plus 8 is minus 8I is equal to 0. Or we get it as I is equal to minus 6 by 8. Right? Minus 6 is equal to 8I, or I is minus of 6 by 2 is 3, 8 by 2 is 4, minus 3 by 4, or minus 0.75 ampere. So I is this much. So you are asked to find out Vx. Vx is equal to 4I, which is equal to 4 into minus 3 by 4, so minus 3 volt. Right? So this is the answer which we have got. So this is how we have solved the example, where here you had independent and dependent sources, both are there, right? So this is how the whole problem has been solved. So you can see more examples here. More examples can be solved on source transformations. Always keeping in mind that the element through which, in this case, the element which was controlling element was 4 ohm, because the voltage across it, that is Vx, is what was controlling the current source, right? So that has been retained till the end. It has been, this element has not been changed, and it has been retained as such. So this is something which we have to be careful while dealing with dependent sources. This is about source transformation. Okay, so here we have some problems. Here you are asked to find out the current in the 6 ohm resistor using source transformation. So you can do source transformations and simplify the circuit, and finally find out the current through this particular 6 ohm resistor. Some points which we keep in mind is, if you are asked to find out the current through a particular element or the voltage across a particular element, then you keep the element as such, and till the end of the problem, and then you and do source transformations with other elements. That is one point which we normally keep in mind while solving such problems. Again, here you are asked to find out the power delivered by the 50-volt source. Now the 50-volt source is this one. So you have to, since you are asked to find out the power is equal to V into I. V is 50 volt, and current you can find out by solving or simplifying the remaining part of the network. Now, since the power delivered by the 50-volt source is ours, do not do a source transformation over here. Since we are working on source transformations, normally our tendency could be 50 volt and 5 ohm are in series, but do not do a source transformation over here. Uh, you can do source transformations with the other elements and simplify it, find out the total current through the network. And once you find out the total current in the network, that voltage into the current will give you, voltage will be 50 only, uh, obviously, and multiplied with the current will give you the power delivered by the source. So keep this in mind while you are asked to find out anything like this, like power or current for a particular element, then that element is normally retained. Likewise, do not do source transformations on those particular elements. Okay, so please do as many problems as possible with source transformations. Source transformations make our life much easier. So in some cases, rather than solving it using KVL equations, so you actually do not require equations or something. It will be mostly by using source transformation, you can simplify the network just by series parallel combinations and source transformation only, and solve the circuit. So source transformations are very useful when we solve for complicated circuits. Okay. So fine. Thank you.